So now that we've progressed through all the ideas in the course, what we're going to do is step back from the kind of details that we've been in and scale up to the bigger picture. And we're trying to do a course review or overview to remind ourselves of the bigger picture of what did we talk about and what did we learn in this course. Again, scaling out from looking at the fine details to what do we try and cover. So in general, this course was all about modeling some y as a function of x's. The reason I put y in quotes there is that we started with linear regression, where we're modeling the mean of y, right, the mean of a numeric variable. Then we moved into logistic, where our y was something like disease, yes or no. And we modeled the log of the odds of y equaling 1, right? Or the log of the odds of the disease as a linear function of x's. So I tried to write it in quotes just to generalize. We model y, or some summary of y, as a linear function of x's. Then through the course, we broke these models down into one of two kind of broad goals. So the first is fitting an effect size model. And here, the goal of a model like this is to try and estimate the effect of some variable x1 on y. And we're going to need to control, or we could say adjust, for other variables x2, x3, all the way up to xk. So adjust for things like confounders, deal with effect modifiers, and so on. Right? We talked about different types of variables we might want to include or exclude from an effect size model. So really, the goal there is trying to estimate B1, get an unbiased or least biased estimate of the effect of x1 on y, controlling for other variables. And there we saw that we can think of B1, the estimate we get in data, as being equal to beta 1, the true effect. Right? So we like to think out in the world, there is some true value or some true effect that x1 has on y. Right? Our estimate in the sample of data is going to be equal to the true value plus some random error. Right? So some random error due to being a sample, not the entire population, plus some bias. A bias due to confounding or collinearity or other things we've explored. So our goal is really to try and remove this or make this as small as possible. Okay, so to try and eliminate as much bias as we can. Error is always going to be there. Right? In a sample of data, there's always going to be some error or variability, but we can deal with that. We can model that. Right? We've learned how to estimate standard errors, build confidence intervals, things like these, things that capture the measure of uncertainty. So our estimate is the true value plus some noise or some error, and we can deal with that. Our focus was on how to identify variables that may be introducing bias and try and address those. The second goal, and this got relatively much less time in our course, we really focus on trying to estimate the effect of some variable on an outcome. But we also did talk a little bit about the idea of predictive models. And these are where we're trying to get a good prediction of that y variable. So here we're trying to think about which variables will be good at predicting, which variables are good at predicting that outcome. So we're trying to maximize predictive power of our model. And so here, the focus of a predictive model is really on the outcome, right? Our estimate of the outcome, and trying to get the best prediction we can, or a prediction with the smallest amount of error. And so this was kind of the theme throughout the whole course. The type of variables we were working with changed. We looked at numeric variables, disease, yes, no, those type variables, rates, as well as times till death. So what I'd like to do now is talk a little bit about each of the regression models we went through, again at a higher level, bigger picture, but trying to recap some of the ideas we went through this course as we talked about these different models. So in the start of the course, we started off with looking at numeric outcome variables, and specifically talking about linear regression. And we started by saying, if we have some numeric outcome, this type of variable can be summarized using a mean. Mu of y given x is the way we look at it. The mean of y, and I guess the given x is going to be once we include x variables. So we can summarize numeric variables using means. And what we learn to do in linear regression is model that mean of y. So model the mean of y as a linear function of the x variables. The mean of y given x, b naught plus b1 x1 all the way up to bk xk. We can look at the model in this way, regardless of if we're trying to predict the outcome variable, or if we're trying to estimate what effect does x1 have on that outcome. Right, so we can look at the model expressed this way, regardless of if it's a predictive model or an effect size model. But we did see, focusing on effect size models, that this coefficient here can be thought of as how does the mean of y change for one group versus another. So if x1 is just a exposed or unexposed, what's the difference in the mean y for exposed relative to unexposed? And we saw interpretation of this change if x1 was a numeric variable, if it had more than two groups. But this is the essence of it. This coefficient tells us how does the mean change when x1 changes. And then looking at this, we saw, I'll just add those over here, some extensions. So throughout the course there was a lot of core material, and then there was a lot of extras of things that were nice to know but not need to know. So not part of the assessment. But we talked a little bit about the idea of rather than modeling the mean of y, we could say use something like quantile regression. And with this we can model, say, the median of y as a linear function of the x's. So rather than trying to model the mean of y, you can model the median of y using a linear function of x's. And we really only mentioned this in name, but it's an extension of linear regression. So once you understand linear regression, understanding quantile regression is not a big jump from there. And just to kind of extend this, you don't need to only model, or it can model more than just the median of y. It can model any quantile of y, okay, or any percentile of y as a linear function of x's. So again, what I mean by that is, right, the median is the 50th percentile. We could say model the 80th percentile of y as a linear function of x's. So this was a topic that you could look at on your own if you wanted to. We didn't really get much into it, but as I mentioned again, the kind of theme of the course is we lay a foundation for certain topics, and then I spend time saying, here's all the kind of extra paths or extensions you can read about if you want to deepen your knowledge around this area. After our discussion of linear regression, then we moved into talking about logistic regression. Right, and here was where our outcome variable was a yes-no binary or dichotomous variable. So does someone have a disease, yes or no? And we saw these types of variables, the categorical variables. One natural way to summarize these is using a proportion. And there, right, probability of y given x, or we just started to label it as p, removing the y given x subscript, just to trim down some of the notation being used. We saw that in logistic regression, we can think of this two ways. We can think of it as we're going to model p, right, the probability of getting the disease, as a logistic function of the x's. So that looks like this here. Model p, right? What's the proportion with the disease, or the probability of getting the disease, as a logistic function. E to the b naught plus b1 x1 all the way up to bk xk over 1 plus e to the b naught plus b1 x1 all the way up to bk xk. This was one way of thinking of the model. Right? We're modeling what's the probability of getting the disease as this logistic function, tends to form a sort of S-shaped curve. Or right, we can think of this same model as being that we're going to model the log of the odds of y equals 1, right, or the log of the odds of the disease as a linear function of x's. Okay, so again, expressing that, you can think of it as modeling the log of p over 1 minus p. Okay, what are the log of the odds of getting the disease as a linear function of the x's? And now, expressing the model on this scale, the log of the odds, allows us to link to, okay, or connect to a line or a linear function. And we've learned a lot about linear functions and how to work with them, using linear regression as our basis to build that understanding. And so again, remember, these are the same model. One expressed on the scale of the probability of disease, one on the scale of the log of the odds of disease. And while they're the same model, we saw that expressing it on this scale is a bit more useful way to think of it for a predictive model, where our goal is sum in a bunch of x's, estimate what's the probability of the outcome happening. Right? So if we're trying to predict whether or not the outcome will happen, this is a good way to look at the model. If we're building an effect size model, looking at the model expressed on this scale, the log odds, is a nicer way to look at it. Although it's important to stress, these are the same model. And we saw, when doing that if we exponentiate this coefficient, it's going to give us the odds ratio. What effect does x1 have on the log odds? What's the odds ratio associated with x1? Adjusted for x2, x3, and so on. And just a quick note, when talking about linear regression, we saw this coefficient gave us a difference in means. I might have forgot to say there that it's adjusted for these other variables. So I just wanted to quickly mention that in case I did forget to say that. And then a few extensions we saw. And so again, these were mentioned mostly in name, left for you to explore if you want. Some extensions of the logistic model. We saw in name multinomial logistic regression. Sometimes this gets called polytomous logistic. This is where we have more than two possible categories. So rather than disease, yes or no, we're trying to estimate, say, which province does someone live in? Or if you want to put it in an American context, which state are they in? Right? So something that has more than two categories, but unordered, no ordering to them. And that's where the other extension we mentioned comes in, ordinal logistic regression. And this is where our outcome variable has more than two categories, and there is an ordering to them. So not diseased, mild, severe, something like that, right? Where there's more than two categories, and there is a ranking or an ordering to them. So again, these were mentioned mostly in name. I believe one of the R scripts we had may have had some R code to explore some of these on your own if you wanted to dig a little bit deeper. One thing I hope you're seeing through the course as you've learned about linear, then logistic, then Poisson regression, then survival analysis, is that while all these models are different, they're also, when you kind of zoom out, they're all pretty similar or almost the same in concept. So if you've got a decent understanding of logistic regression, understanding multinomial logistic or ordinal logistic is not a big jump from where you are now. It's just learning a little bit more about how these models differ when we have more than two categories or when there's an ordering or ranking to them. After logistic regression, we moved into talking about Poisson regression. And that was where our outcome was a count variable. So counting how often something occurred. How many people got a disease? How many car accidents were there at an intersection? How many people showed up to the ER? Things like these. And we saw that counts, one of the natural ways to summarize these is we summarize them using a rate, which is y over t, the number of occurrences per unit time. And again, the rate is a mean, right? It's the average number of occurrences per unit time. And we didn't mention this when talking about logistic regression, but the proportion can also be thought of as a mean, right? It's a mean of zeros and ones. Poisson regression, we saw that here what we want to do is model the rate or the count. So I'll express everything in terms of the rate, but we want to model the rate at which things occur, or how often it occurs, as an exponential function of the x variables. We can think of that we're modeling the rate as e to the b naught plus b1 x1 all the way up to bk xk. So this is looking at the model on the scale of the rate at which events are occurring. Or we said we can also think of modeling the log rate. So we can model log rate as a linear function. So again there, we're modeling the log of the rate at which events occur using a linear function of all the x variables. Okay, and again, at this point in the course, things are starting to look a bit repetitive and familiar. I want to put a reminder here. While these are the same model, again, just expressed on the scale of the rate or the log rate, looking at the model expressed on this scale is a bit more helpful when building a predictive model. So if we want to try and estimate what is the rate at which things are occurring, we can sub in a bunch of x variables and try and estimate that. If we're building an effect size model, where we want to say what effect does a particular variable have on the outcome, looking at it on the scale of the log rate can be a bit more helpful. And we saw that, again, exponentiating this gives us the rate ratio adjusted for x2, x3, and so on. So it allows us to estimate what effect does x1 have on the rate adjusted for other variables, or estimate the rate ratio adjusted for other variables. The way we went about building our model selecting variables is pretty similar, pretty much the same for all these regression models that we looked at. In a second, I'll mention some of the extensions we explored. Before that, I want to put a few notes. There are a few notes about how these differed a little bit from linear or logistic that we've seen so far. So some things that made Poisson data or count data and rate data a little bit different is first the idea of individual versus aggregated data. So we saw that we can count how often the event occurs for an individual, or if events are rare, if they're not going to occur very often, or they can only occur once, like say death, if we're looking at death rates, then we need to aggregate. We need to put people into groups and look at how many deaths occurred within each group, and then how many person years exposure were there, or what's the kind of measure of time or exposure for that group. But so that was one way it differed. Data can be on the individual or aggregated level. And we can be looking at counts or rates. Again, if everyone had the same amount of follow-up time, we can look at the counts. So if we're looking at the number of visits to a physician in a year, and everyone has been followed for 1 year, we can just compare the counts, or the number of visits. We can just compare that to y for each other. If people have different follow-up times, say if for me we've recorded how many times have I seen a physician in the last 3 years, and for someone else, how many times have they seen a physician in the last 6 months, we have different follow-up times, we have to model the rate. So this gave us the idea of having to use an offset. And we talked about exactly what an offset is when we were in Poisson regression, but I just wanted to bring up these notes or these reminders of how Poisson regression differed a little bit. We had those kind of things to think about. Now, some of the extensions that we talked about, and again, these were mentioned as things you can explore on your own if you want. They're not stuff we talked about very much in depth in the course. The first was negative binomial regression. We said this is essentially very similar to Poisson regression. It allows us to estimate the rate as a function of x's, or the log rate as a linear function of x's. But where it differs is that it does not require the mean to be equal to the variance. So in negative binomial regression, it allows us to get separate estimates of mean and variability. If you remember, a feature of Poisson regression was that the mean is equal to the variance. So it allows us to estimate those two separately. And then we also talked a bit about the idea of zero inflated Poisson. So if we have excessive zeros, or the event is not occurring for more people than would normally be expected, we can use zero inflated models. There's zero inflated Poisson, and we also mentioned briefly zero inflated negative binomial. This allows us to address the excessive zeros as well as estimate the mean and variability separately. So again, those are topics you could explore on your own a little bit more if you wanted to. Our final topic for the course was survival analysis. And there we're looking at an outcome that is a time till an event occurs. And the kind of unique thing about survival analysis is that outcome actually has two components to it. The time someone was followed for, and an indicator of whether or not the event occurred. The event occurred, or if they were censored. We can summarize using a hazard. And then a hazard also is pretty similar to a mean. It's a rate at which events are occurring. And we saw within survival analysis, and I'm going to talk mainly about the survival regression models. We talked about not the Kaplan-Meier model. We'll come back to that in a moment, but I want to stay on the theme of regression models that we've looked at. So we saw we can model the hazard as an exponential function of the x's. So we can be modeling the hazard as e to the b naught. And I'm going to put that in quotes. We talked a bit about how the idea of the intercept changes depending on exactly what model we're using. So let's just put it in quotes there. B naught plus b1 x1 all the way up to bk xk. And then just a reminder here, right, that the way we can use this is we fit a regression model that estimates the hazard as a function of the x's, and then the survival function, s at t, the probability that the survival time is greater than little t, is e to the negative hazard times t. So we estimate the hazard as a function of the x's, and then we can sub that in here to get the survival function, the estimated survival function. So again, looking at it on this scale is a good way to think of it when we're thinking of a predictive model. If we want to try and estimate what's the probability of surviving beyond a certain time point, we can use this model to estimate the hazard, then sub it in there to estimate the survival for that individual. Or we also saw, we can think of it as we're going to model the log hazard as a linear function of the x's. The log hazard is b naught. I'll put that in quotes, right? We talked about how exactly what that intercept or b naught term is changes depending on if we're looking at an exponential model or Cox proportional hazard model and so on. b1 x1 all the way up to bk xk. Again, thinking of the model on the scale of the log hazard is a good way to look at it when we want to talk about an effect size model. And we saw this coefficient here. If we exponentiate that, it's going to get us a hazard ratio adjusted for x2, x3, and so on. Right, so again, we can estimate what effect does x1 have on the hazard, adjusted for other variables, right, adjusted for confounding and so on. This differed a little bit from linear or logistic or the other models in a few ways. What made this unique? Well, this also has a time component to it, which linear regression did not. So just a few notes on this. First one is that our choice of this b naught term is different for the exponential, the libel, Cox proportional hazard, So that's how these models differ. Is the intercept term changed a little bit, but by putting it in these kind of quotations, what I want to do is show that what we're looking at here is another generalized linear model, pretty similar to all the ones we've seen in the course before. And we had some lecture time where we talked about how this term changes if it's exponential versus Weibull versus cost proportional hazard and so on. Another note is that we also discussed the Kaplan-Meier model. And that's not presented anywhere here. These are all looking at regression models. Right? The Kaplan-Meier model is not a regression model, although it is another useful model for survival analysis. So that's why I've left it off writing it here, because I really wanted to try and connect the dots on all the different models we've talked about. And that one was a little bit different in terms of it wasn't a regression model like these are. And then some of the extensions. And again, these were very much left for you to explore on your own if you want to. We didn't get into the details of any of these. The first was looking at time-dependent coefficients or parameters, these B's, allowing these coefficients to change over time, and allowing B1 to depend on time or change over time means we're allowing the hazard ratio to change over time. So we talked a bit about that as an extension for dealing with non-proportional hazards. And then the other extension that we mentioned, mainly just in name, is time-dependent covariance, or the X variables. So allowing X variables to change over time, allowing the dosage of a drug that someone's getting to be different over time, or allowing people to switch from one treatment to the other over time. So these are kind of all the regression models that we looked at in the course, kind of zoomed out on a higher scale, or the bigger picture. All of them are, well, maybe not all, let me say it this way. The first one we talked about, linear regression, that's a linear model. Logistic, Poisson, and the survival models are all generalized linear models. We did some generalization to kind of the outcome or the y that we're interested in order to link to a linear function. So the point of me saying this is to try and remind you that the way we go about building our models, selecting variables, it's all the same in concept. And so depending, is it a predictive model or an effect size model? If it's an effect size model, the idea of confounders, effect modifiers, collinear variables, independent predictors, mediators, all these sorts of things, they're all the same in concept. The way we can go about checking for them and deciding if we should include these variables in our model or not is pretty much the same regardless of if we're working with logistic regression or linear regression. So it doesn't really depend on the type of model. The sets of assumptions for all these different models, again, we're pretty similar with slight changes depending on the exact details of the model. We always had this assumption that the left-hand side of the equation, so whether it's the log hazard or the mean of y or the log odds, is a linear function of the x's. So we assume linearity. And the way we checked that was similar. It differed a little bit for logistic, but in concept it was always kind of the same. And if linearity was not met, the way we addressed that assumption was always the same. Right? We could categorize x. We could include polynomial terms. We could try transforming it. So the point of all this is to say that the way we build models, select variables, go about refining them, and so on, is the same in concept and very similar in practice in the details of how we do it, regardless of the exact type of model we're working with. So we'll take a few minutes to remind ourselves of the approach to model building and variable selection. Again, staying at the kind of big picture level, not getting into the fine details. So the first was we talked about effect size models. And there we talked about different types of variables that we may want to look for and include or exclude from our model. And the first idea was confounders. And there we said kind of the classic diagram is that there's some variable x2 that has some effect on x1, our variable of interest. Okay, so maybe I should put a reminder up here. X1 we're labeling as our variable of interest. Okay, so what effect does x1 have on y? x2, x3 we're using to indicate other variables not our variable of interest. So x2 has some effect or is associated with x1. What effect does x1 have on the outcome? That's our question of interest. x2 also affects the outcome. And if there's a variable x2 that's a confounder, we're going to want to include this. We're going to want to adjust for confounders. Then we saw the idea of mediators. Mediators numerically behave the same as confounders, but they're not the same. So the idea of a mediator is x1 directly causes x2 or has some direct impact on it, and then x2 affects the outcome. x1 may also independently affect the outcome. So here x2 is sitting on the pathway between x1 and y. x1 leads to x2, which then leads to the outcome. And for these, we generally want to exclude them. And we talked a bit about how it's a little bit more complicated than just saying include or exclude, but we want to exclude if we want to estimate the total effect. And so we mentioned the whole idea of mediation analysis is sort of a subtopic. You can read about it on your own if you want. It's not something we've talked about in the course. We stayed at the level of saying, if we want to know what's the total effect that x1 has on y, we should exclude x2. If we include x2, B1's only going to tell us what effect does x1 directly have on y, not the effect that goes through x2. We talked about the idea of collinearity, and this we were saying is where it's not mediation. x2 has some effect on x1, but it's a really strong association. So I'm just picking that by drawing a really thick arrow. x1 and x2 are so highly associated, you cannot really separate them. So this happens quite often when x2 is an alternate measure of x1. Okay, or it's capturing the same, almost all the same information that x1 is. And we saw that we're going to want to exclude these. So if you have some variable that is almost another measure of x1, we don't want to put that in the model. We talked about the idea of what we called independent predictors. Sometimes these just get called risk factors. So our goal is to estimate what effect does x1 have on y, and there's some other variable x2 that's not associated with x1, but also able to predict the outcome. And these we said there's arguments for including them and arguments for excluding them. If x2 is a strong predictor of the outcome, that's a good argument to include it. It often will also decrease the standard error for B1. If x2 is not a confounder, it doesn't need to be adjusted for, and that's the argument for excluding it. So we kind of talked about the pros and cons of each of these. We won't get to redoing that whole discussion there. And then finally, there's the idea of effect modifiers. We want to know what effect does x1 have on y, and there's some other variable x2. It's not on the pathway between x1 and y, but the effect that x1 has on y changes depending on the values of x2. So if we want to say what effect does x1 have on the outcome, we need to specify the effect of x1 when x2 takes on certain values. And again, these we want to include. If the effect of x1 on y depends on some other variable, we want to state what is the effect of x1 given the values of x2. Then we spent less time, but we also did talk about predictive models. And here we said really our focus is on including significant and strong predictors of the outcome. So our focus is not on these about the idea of confounding actually does not exist in a predictive model. But if we're not going to interpret the effects of certain variables, it doesn't really make sense to say the effect of two variables are stuck together. So there, we're really trying to include variables that are good predictors of the outcome, variables that are reliably measured, that are available at the time of prediction. So at the time we want to make the prediction, can we actually get these variables measured? We can use things like the likelihood ratio test, right, to test adding variables if they significantly improve the model, We can also use things like AIC or B.Sc, again, to evaluate which model seems to be the best. So there's certain other criteria to deciding which variables should go or not go into a predictive model. And then a few things I wanted to say, regardless of if it's an effect size model or a predictive model. It's important to remember that the order that we test including variables in does matter. So for example, it might be the case that there's variable x3 and x4. And whether it's predictive model or an effect size model, we might need to include one of them, but not both of them. So if we include x3, we don't need x4. If we include x4, we no longer need x3. So these two variables contain almost the same information. Now, if we put x3 in the model first, we're probably going to find we don't need to include x4. Where if we put x4 in our model first, we might find we don't need to include x3. So just a reminder, the order that we include variables in does matter. And so that's why we said throughout the course, model building, variable selection is kind of half science, half art. But so I won't get into going through that whole conversation again. This is supposed to be a review and a summary. But that reminder, the order that we include things in does make a difference. So we don't want to get too stuck on this. Is our p-value, say, less than an alpha of 5%? We've talked in the previous course and this how p-values are useful as a tool to help, sort of as a screening tool, but we don't want to get too stuck on this magic p-value, greater than or less than 5%. P-value of 4%, p-value of 6%, they're pretty much the same p-value. So we want to use p-values as a guide and a tool to inform our decision, but not getting too stuck on what is the exact value of that p-value. We also talked about the idea of if there is interaction or effect modification, different ways to approach that problem. We can stratify on that variable and fit separate models within strata, or we can model it using an interaction term or an effect modification term. And we really look at these as two separate ways of trying to address the same problem or deal with the same thing. Another important thing we try to stress throughout the course is that the initial data exploration is very important. Looking at univariate summaries, bivariate summaries, really exploring the data helps inform the model building procedure. So it really helps you notice what things do you need to address and help you identify nonlinearities or influential points. And on that note, the idea of sensitivity analysis is also important. If we have a nonlinearity, say if the effect of age on the outcome is not linear, we can try including polynomial terms, fitting the model, or we can try categorizing age and fitting a model. And hopefully we'd see our result did not change very much depending on how we've addressed that nonlinearity. So seeing it's not sensitive to the solution we've used. Then the final thing I want to say on this is we talked a bit in the course as we worked through analysis and then writing papers based on those, is that the stroke guidelines can be quite useful for writing your paper or for critiquing paper. Right? So these are helpful in knowing what should go into a paper based on observational data. Now just some closing remarks I want to make before we wrap all this up. What I hope you got out of this course is I hope that you got a solid foundation in regression models, in building them and interpreting them and so on, with the kind of caveat that we talked about a lot of ideas at once. We tried to talk about concepts and the actual computations as well. But what I hope is you have a solid foundation that you can understand these models and you can build on your knowledge and expand your knowledge when you need to. That you have the foundation, what is a regression model, and you can build on top of that when you need to. I hope you understand that all these models have assumptions and they're never perfectly met in reality. So we want to know, are they reasonable to work with? Knowing that the linearity assumption is one of the key assumptions or one of the most important assumptions for us. If that assumption is not met, things fall apart, whether they're predictive models or effect size models. The other assumptions can be pushed a little bit more. I hope you've got a balance between knowing what to do with certain data, how to do it, and how to interpret it when it's done, regardless of what end of that spectrum you're on, whether you're more of a producer of statistical analyses or a consumer of them, that you've gotten all the different points on that spectrum and are able to work with those. I hope you're comfortable in working with the statistical software R and in being able to get some of these analyses done. And I hope that you now have a few more tools in your toolbox to try and attack analyses when you need to. Two closing remarks I want to finish off with. The first is that I hope you remember the quote that all models are wrong, but some are useful. Right? And I think that's really the case. And I hope you really see this course as the foundation that you can build on, but knowing that when you run an analysis, you're almost surely going to need to take some of these methods and extend them or build further on top of them, and that this really is the foundation for regression modeling that you can build on top of. Well, thank you. I hope you enjoyed the course.
Stick around, guys, because we got lots more. Statistics is almost as beautiful as a unicorn.